Hi, welcome back. Last time we were talking about partial derivatives and how we could calculate those and what those looked like in terms of being on a surface. As you remember, we were talking about our surface, we were talking about taking a plane, slicing our surface, and following along this curve and asking what is the slope of the tangent line here if we're walking in the x direction and keeping y fixed. That was how we calculated df dx. And then we asked in terms of if we kept x fixed and we let y vary, that would tell us what df dy is equal to. You can see in both of these examples that the slope of the tangent line is negative, right? The z value is decreasing in the direction, in the positive x direction, and as we walk in the y direction, the slope is also decreasing. So at this point, the xy point, the AB point, we have that this partial derivative with respect to x is negative, and the partial derivative with respect to y is also negative. So we're going to now take these two concepts and put them together, and here I have a better drawing than I did by hand, where we say, all right, this df dx, slope of this red vector. Df dy, slope of this blue vector, where we have the change in z divided by the change in y. And so if you look at these vectors, we can think, oh, those vectors, they lie in a plane. And this idea of these vectors lying in a plane is the analogous idea of our function of one variable, where we have at a point, we can talk about the tangent line to the curve at that point. Here we now have a surface, so the thing that's tangent to the surface is not a line, it's now a full plane. And so it's a natural question, well, what's the equation of this plane and how can we use it? All right, so if you want to really think about this as visually, conceptually, you zoom in to your surface as far as you can, right? In our, if we even, for any even really curvy function, if you zoom in here, and then you zoom in even further, and you zoom in, the more you zoom in, the more the function looks like a straight line. Well, the same thing happens on a surface that is sufficiently smooth. The more you zoom in, the surface is going to look more and more like a plane. All right, and that's the idea here of the tangent plane. But not only that, let's say we chose some other curve here to approach our point. Right, so remember this is the point AB, and what we're doing is maybe we came along a curve to approach AB. Well, on the surface of the on the surface, the curved surface here, then this green curve would translate into being a green curve on the surface. And not only is it the case that the red line, the red vector and the blue vector lie in the tangent plane, but also the tangent, the vector tangent to the curve at that point also lies in this plane. So that's another aspect of this tangent plane really being a good representation of the surface, because any curve going through our point AB in the xy plane is going to have as its tangent vector of that corresponding curve on the surface of the curve that's on this surface, that's the graph of the function, that is also going to have as its tangent vector, it's going to lie in that plane. All right, and so when we put all that together and talk about our idea about what it is for a function to be differentiable, right? When we're talking about limits and functions of of limits of a function of multiple variables, where you need to be able to go along any path. Well, you bring all these ideas together, and you say, if if you can have this limit that exists along every path, then this tangent plane looks a whole lot like the surface when you're very close to AB. And so this key idea, which will manifest itself in a couple of different ways as we go forward, is going to say the tangent plane is a good approximation for the surface when we're close to the point. And we're also going to say that the function is differentiable at that point. So how are we going to prove that things are differentiable? The shortcut we're going to use is to say, if both partial derivatives exist near AB and they're continuous at AB, that's when we're going to say that the function is differentiable. If you're interested in understanding this at a deeper level, you would want to go ahead and take a real analysis class and start to really dive deeper into these definitions to talk about when a function is differentiable, what does it mean to be differentiable at an even deeper level. But what we're going to do is we're going to focus on taking the partial derivatives, checking to see that they exist and that they're continuous. And if that's the case, we're going to say the function is differentiable at that point. All right, so how do we come up with the equation of the tangent plane? I've got a really simple equation here, but let me just give you the intuition for what's happening here. Let's look at this, our tangent plane, and let's talk about what the normal vector to this tangent plane would be. All right, so the normal vector to this plane well, it's going to be, so now let's talk about the equation of the tangent plane. Here is, it's a rather simple equation that comes here, and here's the way I like to think about it. So here is z minus z naught, where we're basically creating the point slope version of the tangent plane, where we talk about how far away from z are we? From how far is our function value away from near our initial point z naught? Right. This being the tangent plane above above our point here. If this is x naught, y naught, then up here this is the point x naught, y naught, z naught. And what we're saying is how much, if we walk in the x direction, right, and that's sort of this red thing here, if we walk in the x direction, how much does our z value change? Well, the amount that it should change if we walk in the x direction is dependent on the slope in the x direction, which we said this is our slope in the x direction. How much does the function change if we only move in the x direction? So this relates to the slope of the function in the x direction, whereas if we're going in the y direction, how much does the function z change if we go in the y direction? Well, that's what happens here. If we walk a little bit in the y direction, how much does the function change? Well, this is the rate of change. The partial derivative is the rate of change of our function if we walk in the y direction. So really, this is really close to the way we write down our equations of tangent lines in the standard two-dimensional space, where we write y minus y naught is equal to the slope dy dx times x minus x naught. right? So this looks exactly like that. So now that we have that, so let's do an example. Let's do an example where we use the equation of the tangent plane to write down the formula for what the tangent plane to this curve is. Z is equal to x e to the xy at a particular point. I'm going to skip a few slides here and talk about what our game plan is. So if we want to figure out the equation of the tangent plane to a curve, then we need to know what the partial derivatives are and evaluate them at our point. So that's calculating the slopes at those things. Here we have x naught and y naught, but that doesn't mean we have z naught. We have to calculate z naught. That's what the second point is here. And then once you have your point, x naught, y naught, z naught, then you can use those to plug in and get the value of that we can have our equation of the plane. All right, so let's calculate the partial derivatives. dz dx is equal to, well, this is a chain rule, right? It's x times a function that includes x. So we have first times the derivative of the second, so that's y e to the xy, plus the derivative of the first times the second, e to the xy. So what do we get? We get xy plus 1 times e to the xy. And that's the partial derivative of z with respect to x. And then the partial derivative of z with respect to y. Now in that case, x is just a constant. So we're basically dealing derivative of a constant times e to the xy. So we have to bring down the constant, we get x squared e to the xy. So those are our two partial derivatives, and now we have to plug in our point 1, 0. So if we plug in so dz dx at 1, 0 is equal to, well, we plug in y is equal to 0, e to the 0 is equal to 1, and the derivative with respect to y, x is 1 times e to the 0 is also 1. So dz dy of 1, 0 is also 1. So those are our two partials. Now we need the point on the surface. So what is z naught? Is equal to the function of x naught and y naught. So we get 1 times e to the 0, which again is 1. So our point on the surface is 1, 0, 1. And now we use those to write the equation of the plane. So we get z minus z naught, which is 1, is equal to 1 times x minus x naught is 1, plus the slope is 1 times y minus 0. So we get the equation z is equal to, let's see, x minus 1 plus y plus 1. So z is equal to x plus y is the equation of the plane. Right, and then remember, recognize this does look like the equation of a plane where we specify x and y as a function of z, and every coefficient is some constant. All right, let's pause for there and come back shortly. All right, talk to you soon.